Okay, we'll be differentiating this function, and notice we have this minus that. So we just have to differentiate the first and then minus the derivative of the second. And here we have x times inverse tangent x. So to differentiate the first part, we will have to use the product rule. So product rule in the action first. Let me write down y prime. Product rule says I will have to write down the first function, so that's x. And then times the derivative of second. Derivative of inverse tangent is 1 over 1 plus x squared. And that's it. And then we add it with the second function, which is inverse tangent of x. And then times the derivative of first. Derivative of x is just 1, so we multiply by 1. It's just like that. So this right here is it. And now we are going to minus the derivative of this part. Notice we have 1/2 times that. 1/2 is just a constant multiple. So I will just write this down first. And then we will focusing on differentiating this. The derivative of ln of something, we first write down 1 over the inside. So that's 1 plus x squared. And the chain rule says we have to multiply by the derivative of the inside. Derivative of 1 plus x squared is 2x. So that's what we have. And now let's take a look. This is just 1 times that, which is x on the top, over 1 plus x squared. And this is just plus the inverse tangent of x. And this right here, this and that cancel, and we just have minus x over 1 plus x squared. And we see that this and that are the same, but opposite sign. So they cancel each other out to be 0. So in the end, we do have a really nice answer. The answer is just inverse tangent x. Yeah, so the derivative of this expression is just inverse tangent x. We will be finding the second derivative of the inverse sine x. This notation, d2 over dx2, just means that we will have to differentiate the inverse sine x twice. And if you don't like this notation, you can write down y to be whatever this is. Namely, we have the inverse sine x. And then go ahead and do the derivative. Y prime. The derivative of inverse sine x is 1 over square root of 1 minus x squared. As long as the question doesn't ask you to prove this from scratch, you can just put down the derivative of inverse sine x to be this right here. And for the second derivative, we just have to look at this and differentiate again. But if you look at this as how it is, you will have to use the quotient rule. But it's okay. You know, we can change the form a little bit because I noticed we have a square root. And almost always in calculus, whenever you have the square root or any radical, you should look at that as a power. And this right here, it's the 1/2 power, but it's in the denominator. So I will look at this right here as whatever inside, which is 1 minus x squared, and raised to the 1 over 2, but it's negative because it was in the denominator. And when I do that, differentiate this, we can just use the power rule, bring the power to the front, and then minus 1 right here. And we see that we have negative 1/2, and the inside stays the same. So we write down 1 minus x squared, and the new power, this is negative 1/2 minus 1. You get negative 3/2. However, don't forget, you have to multiply by the derivative of the inside because of the chain rule. Derivative of 1 is 0. Derivative of negative x squared is negative 2x. So this is what we have. And in the end, let's see. 2 and 2 cancel, and then negative becomes positive, so you can cross them out if you would like as well. So on the top, we have the x only, and then I'll write this down to the denominator, and we don't have any more 2's because they cancel already, and the 1/2 power right here becomes a square root, but the numerator here, it's a 3, so I will put down parentheses with the third power. Right, the 1/2 power, it's a square root. And then the 3 is right here. And this right here goes inside. Okay, we'll be differentiate this right here. And notice, even though we have an inverse trig function inside of a regular trig function, we could rewrite that as a regular algebraic expression. But let me tell you, it's easier to differentiate this expression as how it is. So let me show you. I will write down y prime for the derivative, and we first ask ourselves, what is the derivative of cosine? And the answer to that is negative sine. And the inside stays the same. We just put it down right here, the inverse sine x. And then we have to remember the chain rule. Chain rule says we have to multiply by the derivative of the inside, and the derivative of inverse sine x is what? That's something that we have to remember as well. And the answer to that is 1 over square root of 1 minus x squared. And this right here is pretty much it. However, notice this is the inverse sine x inside, and we're doing function composition with the regular sine. So regular sine of inverse sine, they cancel each other. But you still have to remember the result of all this is still an x right here, okay? So this right here is equal to, we have negative x, right? Negative x, times 1 on the top, which is just still negative x, and then over that for the denominator. And we will just write down square root of 1 minus x squared, and that's it. Okay, so it's not that bad at all. We'll find the derivative for ln of x over y that's equal to e to the xy. And we see that the y is not isolated, and I don't think we can isolate the y. But it's okay, because we can just use implicit differentiation. However though, before we do that, we see we have x over y inside of the ln. So by one of the ln property, let's rewrite this as ln of the top, so that's ln x, and then minus ln of the bottom, which is ln y, like that. And then this is still equal to e to the x times y, like this. So this way we don't have to use the quotient rule, right? All right, from here we can go ahead and I will just write down dx to represent that we are taking the derivative with respect to x. And here we go. The derivative of ln x with respect to x is 1 over x. And that's it. You don't really need to multiply by the derivative of x with respect to x, because that's just equal to 1. Anyway, continue. You minus, and the derivative of ln y is 1 over the inside, which is y. But the chain rule says we have to multiply by the derivative inside. Derivative of y with respect to x, that's dy dx. And this is how we squeeze out the dy dx. Earlier, if you put down dx over dx, that's 1. But here we have the dy dx. This is what we need, right? So this is it for the left-hand side. And now, on the right-hand side, we have to differentiate e to the x times y. So first, remember that derivative of e to the something, it always repeats first. So let me write down e to that thing, namely x times y. And now we have to remember the chain rule. We have to multiply by the derivative of this. Well, derivative of x times y, it requires the product rule. So let me multiply, and I will open the parentheses, product rule in action. I will first keep the first function, namely x. And then we multiply by the derivative of the second, derivative of y with respect to x, that's the dy dx business. And then we add it with the second function, which is y, and then multiply by the derivative of the first. Derivative of x with respect to x is just 1. So this is what we have, and this is the calculus step. And then for the rest, we are going to isolate the dy dx, right? And the usual deal is we will collect the terms that have dy dx on one side first, and then just isolate that from there. Before we do anything, let's go ahead and distribute the e to the xy into here. So let's see, here we will have 1 over x minus 1 over y, and this is the dy dx. And this is going to be, let me put down the x first, and then e to the xy, and then the dy dx. And then we have this times that, which is just plus y times e to the xy, like this. And now, these two terms have the dy dx. Let me bring this to the right-hand side so that I can deal everything with positive, right? And then I'll bring this to the other side. So perhaps I will show you guys the work. I will write down plus 1 over y dy dx, and then we'll say plus 1 over y dy dx here. And you see this and that will cancel. That's good. And then I'm going to minus y e to the xy, and then I'll put it down right here. Minus y e to the xy. So that this and that will be cancelled in. That's good. Okay, now let me actually write down this part first on the left-hand side. When I have this plus that, I will factor out the dy dx and put it at the end of the parentheses. So I will write down x e to the xy plus 1 over y, and then we have the dy dx. And this will be equal to 1 over x minus y e to the xy, like that. So this is what we have. And to isolate dy dx, we can just divide both sides by this. So I will just do that right here for you guys. We will see dy dx is this on the top, namely 1 over x minus y e to the xy, and then this is all over that. And let me just write down the 1 over y first because that lines out this nicely, right? So 1 over y plus x e to the xy, right? So that's pretty cool. However, here we have a complex fraction. Let's go ahead and multiply the top and bottom by the least common denominator of the small fractions. We see that we have an x here and we have a y here. So let's go ahead, multiply xy, xy, xy. So in the end, we see that dy dx is equal to, when you multiply this and that, the x cancel out, so we have just the y left. And then we have the minus xy times y, so we get x. And then y and y, you multiply them, you get y squared, and you have e to the xy power, and then this is all over. So I forgot to draw the arrow, but okay. Anyway, take this times that, the y cancel out, so we have x. This times that, it's plus, x times x is x squared, and then we have the y, and then we have e to the xy. So this right here is it. This is the answer. We'll find the derivative for 2 times cosine x times sine y, that's equal to 14. And since the y is not isolated, it's okay because I don't want to isolate it either, because we can use implicit differentiation. And before we do that, we notice we have 2 times this, and that's equal to 14. Let's go ahead, divide both sides by 2 first, so that we can reduce the number a little bit, right? So this is now cosine x times sine y, and that's equal to 7. From here, we can go ahead and put down dx to represent that. We are taking the derivative with respect to x. However, on the left-hand side, we have to do it carefully, because this is cosine x times sine y. To take the derivative of a product, be sure we use the product rule. We are going to first keep the first function, so that's cosine x, and then we multiply by the derivative of the second. Derivative of sine is cosine, and we make the input states the same. And then we multiply by the derivative of the inside by the chain rule, right? Derivative of y with respect to x is the dy dx. And this is how we squeeze out the dy dx. And this is just the first part of the product rule. And then we are going to add the second function, namely sine y times the derivative of the first. Derivative of cosine x is negative sine x. So I'll put down parentheses, negative sine x, like that. And that's pretty much it. And for this, you don't have to multiply by dx over dx because that's technically equal to 1. So that's pretty much it right here. And then the derivative of 7, the derivative of a constant 7 It's just 0, so this is equal to 0. So that's all we have. And now we are just going to isolate the dy dx. We have this on the left-hand side. Let's go ahead and write this down. Cosine x, cosine y. I cannot combine anything because they have two different inputs. I'm not going to combine them neither. So I'll just write this down, and then this is the dy dx. I am going to move this to the other side. This was originally negative because we have the negative right here. Move to the other side, it becomes positive. And we will have sine x times sine y. And then from here, we can just divide both sides by cosine x, cosine y, so they will cancel. And then we do the same thing right here. Cosine x, cosine y. And in the end, we see we have the dy dx being isolated. And sine over cosine is tangent. So the first is tangent x. And then here, this part is going to be still tangent as well, but the input is y. And you can just leave the answer like this. The answer is tangent x times tangent y. We'll be finding the derivative of ln of ln of ln of x. So we'll be using the chain rule 2 times. And here we go. This right here is equal to, as we can see, when we have ln right here, the derivative of ln is 1 over whatever you have inside right here, right? So just put this down right here, namely ln of x, like that. And then the chain rule says we have to multiply by the derivative of this. And the derivative of this ln is 1 over whatever this right here is, right? So I put down that ln inside the denominator here. And lastly, the chain rule says again, we have to multiply by the derivative of the inside here. And the derivative of this ln is 1 over the inside, which is x. So this is pretty much what we have. And that's pretty much it. In the end, we can just put this down nicely. We see that 1 times 1 times 1 on the top is just 1. And then I will put down this x first. So we have x times this ln x times that, namely ln of ln x, like that. And with that, we are done. Okay, we're going to find the derivative of the function 5 to the sine x power. And in this situation, our base is a number, it's just a 5. But the power is a function, namely sine x. So first, let me write down this for you guys. Recall that if today we are taking the derivative of some number b for the base raised to a power x. This right here, we are going to first repeat b to the x power, but we are going to multiply by ln of whatever the base is. So I'll put down ln b like this. So if you guys look at this right here, the derivative of 5 to the sine x power is going to be, this part repeats first, 5 to the sine x power. But don't forget we have to multiply by ln of whatever the base is, if the base is a constant, right? By that formula. And the constant is 5, so ln 5, like that. However, the chain rule says we have to multiply by the derivative of inside. So if you pay attention to the derivative of sine x, which is cosine, I'm going to multiply by that with cosine x at the end, right here. So with that, this right here is it. So this is slightly confusing because I know this right here, it seems that we are doing the chain rule already, but the whole thing is the formula. So you can look at it as how it is, okay? And I will also show you guys the memory device real quick. So the 5 to the some power, I will write it down as 5 to the box power. And then the g function is the sine x. And you see, when you have this form, 5 is the base, and the base is a constant. 5 to this power, the derivative for that is 5 to the box times ln 5. This part is by that. And then g prime, which is cosine x. And now you're going to take this and put it in the box. So we have 5 sine x times ln 5. And then times cosine x. And this right here is the memory device for the chain rule. Okay, we're going to find the derivative of this function. So let's go ahead and start. G prime for the derivative of g. Here we go. Derivative of ln of something. We first write down 1 over this in the denominator. So we will have x plus square root of x squared plus 1. Then the chain rule says we have to multiply by the derivative of the inside. So let's go ahead, multiply by, and open the parentheses. Derivative of x is 1. So let's put down the 1. And then we add it with the derivative of square root of something is first 1 over 2. You open the square root and you put this inside x squared plus 1. However, this is not it yet. Because the chain rule says again, we have to multiply by the derivative of this. And this right here is just for this part, right? Because the derivative inside is only for the square root. So we just multiply this part by the derivative of x squared plus 1, namely that's 2x. And then we will close the parentheses. So be sure you don't close the parentheses here and multiply the whole thing by 2x. The 2x is only for this part because this together, they came from the derivative of square root of x squared plus 1. And now that's what we have. But we can do better. First, we can cancel all the 2, right? And let's see, I'm going to just write this down for you guys as 1 over x plus square root of x squared plus 1. And we'll multiply by the following. Look at the inside. We have 1 plus 1 over this. Well, why don't we just add the fractions up? Well, to do that, look at this one as 1 over, and I'll multiply this by square root of x squared plus 1, and I'll do the same as on the top as well, like this. So, when I do this plus that, I will just have this for the denominator, because I'm adding them up. So let me put down square root of x squared plus 1 in the denominator. And then on the top, you see you have 1 times square root of x plus 1. So let's write that down. And we have plus 1 times x. So this is what we have. And now, is there anything else that we can do? Yes, because look at the top. This right here, square root of x squared plus 1 and then plus x, it's precisely the same as that. Of course, the order of addition doesn't matter, so you can actually cancel this and that together. In the end, you end up with a very nice answer, which is just equal to 1 on the top over this on the bottom. Square root of x squared plus 1, and this right here is it. Okay, we're going to find the derivative of this equation right here. And if you graph this equation, you're actually going to get a heart. So I call this the lovely heart curve. But anyway, that's focusing on the derivative. First of all, we see that the y is not isolated. But it's okay because we can just go ahead and use implicit differentiation. So I will just write this down right here, d dx, and then we are going to get going. So we start right here. We have this to the third power. Be sure you bring the power to the front and then minus 1. Let's do that first. So right here, I will write down 3, open the parentheses, and then this is going to be to the second power now. And the inside stays the same. Namely, we put down x squared plus y squared minus 1. And then the chain rule says we have to multiply by the derivative of inside. So let's go ahead and put down parentheses like this. Now the derivative of x squared with respect to x is 2x, so let's put that down. And then the derivative of y squared with respect to x is plus right here 2y. But because y is a function of x, we are going to multiply by dy dx because of the chain rule. We multiply by the derivative y with respect to x, namely dy dx. And then the derivative of minus 1 is just 0. So this right here is it. We can close the parentheses now. And to continue, this is negative x squared times y to the third power. So we have to use the product rule. And I'm going to pair this up as negative x squared as my first function, and then this is then my second function, okay? So keep that in mind. And you can also put down minus and then look at positive x squared times y squared and do the derivative. Either way is fine. But this is my first function, that's my second function. Okay, here we go. Product rule says, I will keep the first function, namely, I will write down minus x squared, and we multiply by the derivative of the second. Derivative of y to the third power is 3y squared by the power rule, and by the chain rule, we multiply by the derivative y, namely dy dx, like that. Not done yet. We are going to do the second part. We are going to add the second function, which is y to the third power, and we multiply by the derivative of the first. And I take negative x squared as my first function, so the derivative of that is negative 2x. And that's it. You don't have to put on dx or whatever. Yeah, that's equal to 1, so this is it. And we also make this equal to the derivative of 0, which is also 0. And now, this is it. However, I cannot just end the video right here yet because we still have to isolate this dy dx. But it's okay, I will be with you guys. We can do this one together. Let's take a look. We have this parentheses, right? And then this is addition of these two things. And here is the dy dx right here. So what we have to do is to take this thing, multiply in, distribute it first. And let's see what will happen. Just be patient, by the way. This is actually not that bad. If you actually study computer science, if you see the codes, the computer programmers, they have to be extremely patient because the codes are just crazy. This is actually not that bad. We can do it, no problem, okay? Here we go. Take this times 2x. 3 times 2, that's 6, and then we put on the x, and this thing stays, so I'll just write down parentheses x squared plus y squared minus 1, and then square. Next, we take this times 2y dy dx. So 3 times 2 is positive 6, and then we have the y. I will put this down first, so parentheses x squared plus y squared minus 1 square, and I'll put down the dy dx right here. So here is the dy dx, I'll just write it down. And perhaps I will just write down the rest in a nicer way. Here we have the minus 3 x squared y squared, like that, and then we have the dy dx here as well. And this times that, it's minus 2x y to the third power, and all of them, it's equal to 0. And as always, you see that we pay attention to the terms that has dy dx, which is this and that. And I'm going to factor out the dy dx and put it at the end after the parentheses. So let me do this for you guys. I'll open the parentheses. I'll put this down. So just rewrite it. 6y. And you see, it's not a lot of work. It's just a lot of rewriting. Copy things down, right? Yeah, all that stuff. It's just not that bad. Anyway, continue. X squared plus y squared minus 1. And the dy dx will be at the end, so don't worry. And don't forget, this is to the second power, like that. And I'm not going to multiply this power, so don't worry about that. Anyway, this is just the first part. And then we minus 3x squared y squared, and close that. And then we put the dy dx right here. Okay, these two terms, they have the dy dx. They deserve to be stayed on the left-hand side. And I will move everything else to the right-hand side. I will move this first because it was negative here. Once I move this to the right-hand side, this becomes positive. Let me write down positive 2x y to the third power right here. And then I will drag this, put it on the right-hand side as well, and it becomes minus 6x times x squared plus y squared minus 1 squared, like this. And what's the final step? You just divide this on both sides, so you can get the dy dx by itself. So I will finish this with you for you guys. So dy dx, I will write this down again, namely 2x y to the third power minus 6x times x squared plus y squared minus 1 to the second power all over that. And perhaps I'll just write that down first. 6y parentheses x squared plus y squared minus 1 squared, and then minus 3x squared y squared. And with all this, we are done. Okay, we are going to find the second derivative of 9x squared plus y squared is equal to 9. And if you would like, you can isolate the y and things like that, but we can do this implicitly, okay? So I will look at this as how it is, and I will go ahead and write down dx to mean that we will be differentiating this with respect to x. And now here we go. The derivative of 9x squared, you do the power rule, so you get 18x to the first power, and that's it. Next, take the derivative with respect to x of y squared. You first bring the 2 to the front and then minus 1. So you get plus 2y. However, don't forget that the inside function here is y, and we have to multiply by the derivative of y because of the chain rule. So we multiply by the dy dx right here. And this is how we squeeze out the dy dx. And this is pretty much it for the left-hand side. And for the right-hand side, we take the derivative of 9. And this is just a constant, so we get 0 for that. And this is pretty much it for the first derivative. And we can just isolate the dy dx from here, right? Now let's bring the 18x to the other side. So we have 2y dy dx being equal to negative 18x, like this. And from here, we can divide both sides by 2y. So we see that dy dx is just equal to negative 18 over 2 is negative 9. And then we have the x right here over y. So this is it for the first derivative. And to get the second derivative, we are going to look at this right here and then differentiate it again. So let me bring this right here and I'll write it down. We already know that dy dx is equal to negative 9x over y. And to differentiate this, I will just write down d dx like that. And as you can see, the notation-wise on this side, you have d and dy. So usually people will just put down d2y, okay, for the top. And then for the bottom, you have dx dx. This is going to be dx2. You don't need to put down a parentheses. This is actually the notation for the second derivative. And once again, this is the reason why we put down the 2 right here, because you have the d and dy. So you have the 2 right here. And for the 2 on the bottom, it's because we have the dx dx twice, so that's why. And this is the second derivative. Anyway, on the right-hand side, this is a quotient of 9x, negative 9x and y. To find the derivative, we have to use the quotient rule. So I'm going to first square the denominator. Namely, I put down the y and I'll raise that to a second power. And I will bring the bottom function up right here, which is y, and times the derivative of the top. Derivative of negative 9x is just negative 9. And then the quotient rule says we have to subtract the top function, namely negative 9x, and then we multiply by the derivative of the bottom. Here, the derivative of y is the dy dx. Derivative of y is dy dx. And notice, this is just the first derivative. So the second derivative is that, and we do have the first derivative right here. And if you look at this, one of the ways to simplify this is, we already know what dy dx is, which is this right here. So let me clean things up for you guys. Here, this is just negative 9y, and then this is negative negative becomes positive, and we have the positive 9x, and then the dy dx, I will just write it down as that. Namely, we'll multiply by negative 9x over y, and then we divide it by y squared on the bottom, like this. So this is what we have at the moment. And if you look at this right here, we have a complex fraction because of this y. Therefore, let's go ahead, multiply the top and the bottom by this y. Okay? So we are going to have the following. Multiply this y with that, we have negative 9y squared. Multiply this and that, the y's will cancel each other out. 9x times negative 9x. Negative times positive is negative, and then 9 times 9 is 81, and then x squared right here, right? And then on the denominator, we have y squared times y, which is y to the third power. This right here is it, but we can actually do better. You'll see. First of all, on the top, we notice we have negative, negative, and we have the 9 and 81. So let's go ahead and factor out negative 9. And then when we do that, here we will have y squared, and here it becomes positive, and then this is 9, and then we have the x squared, and then this is over y to the third power. When we do that, what is this? Y squared plus 9x squared. It's in fact the original. You see, 9x squared plus y squared. And of course, when you add, the order doesn't matter. So from the original, you see, this right here is nothing but just 9. So this right here is just equal to 9 from the original. So all in all, on the top, we have negative 9 times positive 9, which is negative 81. And then the denominator is just y to the third power. So I'll put this down. And you see that is the second derivative of the original right here. And if you want the first derivative, you have this. And if you want the third derivative, go ahead and do this again.